Hey guys, and welcome back to a new Android and Kotlin video. In this video, I have 5 coroutine and flow anti-patterns for you. So things you should absolutely not do in your code when using coroutines. And because every app out there somehow relies on asynchronous programming, on reactive programming, it's very likely that you're also having some of these anti-patterns in your code. Number 1, if you have some kind of logic in a coroutine inside of a view model on Android, updating some kind of UI state, like mapping a long list of data that somehow does something that is a bit complex and requires a little bit of CPU power. For example, here for this Echo Journal app, which is an audio journaling app, if you play such an echo, such an audio memo, you can see there are UI updates being made consistently here for the duration, for this bar. And in our code, this looks like this. So we are combining multiple different flows here. So the current playing echo idea is an echo is really just an audio memo here. The filtered echo, so we can apply filters. That we have all that in a reactive manner. We just make use of flows. So that's a perfect way to do it. But as you can see, here we are doing a lot of mappings, a lot of very frequent updates, also for these filtered echoes. Whenever we get any new echoes, we filter them by mood and topics. We update our state. We combine them with some kind of other audio track size info flow. And if you just execute this on view model scope here, and this will run on the main thread by default. So yes, it's on a coroutine, but just because you run it on a coroutine, it can still run on the main thread and block your UI and actually drop frames for you, which is very likely going to happen if you have such complex chains of logic here. And that is why the fix and the improvement that is so easy, but so necessary is to execute all that on the default dispatcher, because then you really delegate this work to a background thread. You do need to take some extra care in that case, that race conditions can't happen because you're suddenly using multi-threading in order to update your UI states. But that's something that coroutines are also making fairly easy for us. And this is, by the way, also the app which my new 14-hour premium course, the Android Architecture Masterclass, is all about. So this new course deep dives into architecture, into architecting apps from absolute scratch, and uses this app as the example in order to teach you all those principles on the one hand in theory, but most importantly in the main part in practice. With a real world project, with a real world UI, you get real Figma mockups, which we will then replicate here for this UI. So you can see we can actually record a new audio memo here, blah, 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 and then set this up here. We can play this back. There is so much going on, a multi-table room database. And for the first time ever, you can also get this course for free if you are a member of the Mobile Dev Campus. Alternatively, you can also get it for one-time investment. That is your choice, whatever you prefer. I will include both the links in the video description. Check it out. Coming to anti-pattern number 2 here, and I switched the project for that one. We have a simple data class node that consists of an ID, a title, and a description. We then have a node repository, which in the end just contains an insert node function. And under the hood, the implementation for this node repository may contain some kind of offline first logic, for example, so that the node is first saved in a local database and then in a remote API, so synchronized with the cloud. Then in your node detail view model, you have a function on save node click. So when the user clicks on yes, I want to save the node, then you're just constructing a node out of the current local UI state values. That's all good. You're launching a coroutine in view model scope, and you simply insert that node into your repository, so in your DB, and possibly sync it with the remote API. And if we now take a look in the UI, how we trigger this function in the node screen, here we have the nav controller, we have the view model reference. It's of course very simplified. In a real project, I would not make my screen directly dependent of the view model, but the idea and the problem stays the same, that if we press our button in order to save a node, we call the view model save node click function, and we also navigate back. So you can imagine that you are on a separate screen where you enter the node details, title, description, you click save, and then you also ultimately want to get back to the previous screen while saving the node, of course, correct? Yes, that is correct, but what is the problem here? What is the anti-pattern? Well, the thing is, the moment we call navigate up, our current screen, this node screen where we create this node, is popped from the backstack. If we pop a screen from the backstack, that means the view model associated to that screen will be cleared. So far so good, that is intentional. But if the view model is cleared, then all the coroutines that are launched in that view model in view model scope will also be cancelled, since that's exactly the idea of view model scope, that it just lives as long as the view model does. If you pop the screen, view model scope is cancelled. And if you currently have an ongoing request in here, when you actually navigate back, when you pop the backstack, then this request is cancelled. So maybe if it's fast enough, the node will be successfully inserted in the DB. But I'm pretty sure the call that you make to the remote API to synchronize this node with the cloud that will be cancelled and the node won't be there just because you navigated away and you did not give the view model enough time to actually properly save and sync that node. Now, there are multiple approaches to fix this. On the one hand, one approach would be that you don't call navigate up directly after triggering onSave node, but rather let the view model tell the UI when everything was successful, when the view model is actually ready for being killed, for being cleared, when there are no more active coroutines. That could work, for example, by using a channel together with one-time events. So simply events you send to the UI. You would say, okay, I have some kind of event channel. This would be a channel of some kind of event. You would say, for example, node detail event. This would be a seal interface where you say, okay, one of these events is on node saved. Then you create this channel here. You expose these events as a flow. So we say event channel receive as flow, which doesn't resolve here because this one is unresolved. But this is then the flow you could observe in the UI, listen for these events that the view model could now send after having saved the node. So here you could say event channel dot, I think it's called send, and you say, what did I call it? Node detail event dot on node. And then you can listen to those events here in your UI. And when you receive that particular node save event, then you can perform the navigation in your UI directly. That will be one way of doing it. The other way would be that you don't use view model scope in order to actually insert this node, but rather an application-bound coroutine scope. So instead of this, you can also go ahead and say, I actually have an application class here. So a class that is here inheriting from application that lives as long as your entire Android application does. You're just creating an application scope, actually private, it can be public val application scope. This is a coroutine scope. You say, okay, this runs on, let's say, the default dispatcher by default supervisor job, so that independent children, the children of this scope, so launched coroutines, can fail independently. And this is now the coroutine scope that is by design and by definition bound to the lifetime of your application, since this is where you've created it. And this is now the scope you can also inject in your view model. Application scope, pass in a coroutine scope, pass that in with your DI framework of choice, and then instead of relying on view model scope, you say application scope, because this way the coroutine is not bound to the lifetime of the view model anymore, but to the lifetime of your app. And therefore, if the view model is cleared, this coroutine will still continue running until that node is successfully synced. If you have the question whether you can also use a global scope here, since that is also by definition a coroutine scope that is bound to the lifetime of the application, well, yes and no. Global scope pretty much is the same. Yes, it's also bound to the application. But the thing is, you create a very strong coupling here between the view model and the global scope. If you inject it, you are able to actually replace the instance of this coroutine scope here with another one. For example, if you want to test this code of the view model, then you typically want to replace the coroutine scope or the dispatcher used with one you control in the test case. And that's not possible if you hard code the scope usage here across the app. Also, you're not as free as you are with the My App when it comes to actually canceling the scope. If you want this for some reason, canceling just the children, since that by definition does not work with global scope. So I would advise for the application scope, or alternatively, telling the UI when the node was saved. Anti-pattern number 3. Let's take a look at this little simulated profile API. So we have a remote API, and on the one hand, updating a profile consists of uploading a new profile picture in form of a byte array and just the profile metadata. Let's just leave it at the username, but any kind of details you want to update about your social media profile, for example. So just imagine those suspending functions here would come from retrofit, from Ktor, something like that. And then in your profile repository, you're using this API in order to really combine these calls, because after all, these calls don't really depend on each other, right? So you can make use of parallel calls here, that you upload the profile picture and you update the profile information at the same time. So the calls are overall done much faster, correct? That is very correct. But if we take a look in here, many people misunderstand how they need to do that. So we have supervisor scope. This is a suspending function that gives you a context on a coroutine scope inside of a suspend function. And it's actually meant to let these child coroutines largely here fail independently. So if one call fails, then this won't have an impact on the other call. Here we could also argue that, well, these calls actually depend somehow on each other. So we wanted to cancel both of them if one fails, then we could use coroutine scope. But that doesn't matter for the example and for what I want to show you here. We have a launch block. We have two independent coroutines here. One updating the profile, one updating the profile picture, and we also call join. So we actually block the outer coroutine here, the suspending function, for as long as both of these functions take to complete. So what is the mistake here? What's the anti-pattern, and what did the person who wrote this code did not consider? The anti-pattern is to use launch in order to launch an independent child coroutine that runs in parallel on its own, but immediately calling join after. Or alternatively, what the same issue is if you use async and you immediately call that await afterwards. This is completely against the purpose of independent coroutines, because by default, if we have two such launch blocks, these two calls run independently. They run in parallel at the same time. But if we still want to suspend this outer coroutine, the suspending function here, for as long as both these calls take to complete, then if we simply call join, which waits for a coroutine to finish, this is completely against the purpose, because the moment we call join, which is a suspending function here, we say, hey, at this moment in our code, at this place in our code, wait for this coroutine to finish executing. So we will launch an independent coroutine here. We will update the profile inside that independent coroutine, but we immediately tell it to wait for the execution afterwards. So we don't even get to the point where we can launch the other independent coroutine at the same time, because before we are joining the other coroutine and waiting for the execution. So this way you have sequential code again, even though that was not the intention with these child coroutines. So this is completely equivalent to just calling these functions here directly one after another. This is also sequential. How can we now make use of parallel computing instead? Well, instead of joining here, we want to remove those join functions and join later once we've launched all independent coroutines. So we say we need to keep track of these references, update profile job. We keep a reference of these jobs and upload profile picture job. And then at the end of the execution, where both these launch blocks have already been at least triggered and started, that's the place where we can call update profile job.join and upload profile job.join. This is now correct code. These calls will be executed in parallel. They will finish much faster. And this coroutine will just suspend until both these jobs are complete. Coming to anti-pattern number 4, and this is actually a big one that I see so often. Let's take a look at this. We have a polling task, a suspending function. It enters a while true loop. And inside that while true loop, we have a try and catch block. And what this function does is it just tries to regularly fetch some kind of network resource. So here it just makes this network call, a GET request to this endpoint every 30 seconds in order to maybe just update some kind of local data source. Maybe this API does not offer to actually have some kind of real-time connection to notify the app when data change. So you actually rely on polling that API. It's not too uncommon to rely on something like that. So we keep on making those API calls here. You may wonder, okay, while true is actually always kind of a red flag, or at least something to take a look at. But this coroutine, since it uses delay, it uses a suspending function that is definitely cancelable. The moment we would cancel the coroutine this function runs in, it would jump out of the while true loop here, because if it's stuck in delay and it's canceled during delay, then it will just be canceled since delay is cancelable. Let's take a look at what happens if we execute this here in main activity. So I created a dummy HTTP client here with some logs, so we can also see if the requests are being made successfully. And then I'm launching this here in lifecycle scope. It's of course just to demonstrate this and not because you should really execute something like this on lifecycle scope. Let's launch this app and we will take a look here. You can see the requests are being made. So we do get some data. Here's the JSON response. And every 30 seconds, this would now print another JSON response. So isn't that exactly what we want? Kind of. But what happens if we take a look here in our running devices tab very quickly? You can see this is my dummy app. We take a look at logcat. Let me go back here. And we now rotate the device. So we rotate left, take a look on logcat here. And you can see, oh, what is happening here? Our logcat is being spammed with logs. That doesn't seem to be what we want, right? So what happens here? Why, when we rotate our device, we actually get this infinite spam of logs for our HTTP for each HTTP calls. Well, the problem is that this code is not fully cancelable. So while I told you that both the get function from Ktor and the delay function are cancelable, the thing is, if this function gets cancelled or the coroutine gets cancelled where this function is running in, so this lifecycle scope coroutine we have here, if this coroutine scope gets cancelled, which will be the case if the activity is recreated due to a configuration change like that screen rotation, then the suspending function in there will also be cancelled. And at that point, it's very likely here in this delay function. So this delay function will see, okay, I'm actually cancelled. And since delay supports cancellation, that's all good. So what will happen here and how coroutines work is that this delay function will throw a cancellation exception the moment it is cancelled. And when this delay function throws a cancellation exception, it will be propagated up here. And it sees, okay, our try catch, we catch general exceptions. And because general exceptions include cancellation exceptions, that cancellation exception would be caught here by your own code, by your own try and catch block. And that is why this information that this coroutine was cancelled never reaches this while true loop. So it is technically considered cancelled, but it won't actually, the lifecycle scope here won't ever be notified about this cancellation. It would keep on executing this while true loop. And with every new iteration, it will enter this delay block and it will notice immediately, oh, the coroutine is actually cancelled. Let's throw a cancellation exception. But that cancellation exception gets eaten up again here. It enters the next iteration, enters the delay block here. It immediately checks again, oh, I'm cancelled. Throw cancellation exception. It's eaten up again, and so on. That is why we keep all those logs here in logcat for those HTTP calls. And Ktor does something similar. This get function here checks for cancellation. It sees, oh, your coroutine is actually already cancelled. So I better throw a cancellation exception. But this cancellation exception, again, is eaten up by this catch block. So it never reaches this lifecycle scope coroutine here. And this is, of course, especially deadly when having such while true loops that, in this case, never exit. How do you now fix this? The fix is luckily very easy, but it's something you have to do. And that is if you have try and catch blocks inside of a suspending context. So some kind of function where you can call suspending functions where this is valid. It's always the easiest check to just call delay there. And if you don't get an error, then this is a suspending context. If you are in such a suspending context and you have a try catch block and you catch general exceptions, then you must go in here and say coroutine context and sure active. Because what this will do is it will check for cancellation here when it has caught this cancellation exception in the catch block. And if there is a cancellation exception, if this particular instance is one, then it will rethrow it. And rethrowing it will mean it will then therefore reach the parent scope since it's not caught again by the scope here. Alternatively, you can also rethrow this manually, so you can check if E is a cancellation exception. And if that is, you rethrow this exception. Or alternatively, you can of course also have more fine-grained catch blocks here to not catch general exceptions, but only HTTP exceptions, for example, which would then of course not include the cancellation exception. But if we do this and execute this now, take a look here in our code. Take a look at logcat at our very bottom here. This is our new request being made, and if we now rotate the device, then we're getting new response because the lifecycle scope coroutine starts new, but we don't get this infinite loop of cancellations here, which is exactly what we want. So be very careful with that. Here another little example in profile repository 2. You have some kind of flow that's also suspending context. Here you have try and catch, catching general exceptions. This can also lead to issues. In this case, it would mean if the flow is cancelled, if the flow closes, we launch it in view model scope, the view model is cleared, for example, then the flow would be cancelled, the coroutines in there would be cancelled. These would get a cancellation exception, but the code afterwards would still be executed, even though that shouldn't happen with a cancellation. That is another problem that can happen here. So here, same thing, coroutine context interactive in both these catch blocks, and you are fine. Coming to the last anti-pattern of coroutines and flows, and that is one that requires a bit deeper understanding of coroutines, but one that also very, very many people don't know about. So here we have another profile view model again, and here it's really just some dummy code. We update the profile. I added an exception handler to actually be notified about exceptions for coroutines that are being launched here in view model scope. So we say, hey, this exception handler, please use it together with supervisor job. So supervisor job, in case you don't know, is a special kind of coroutine job where we can say, hey, coroutines or child coroutines of a job that has this supervisor job should actually be able to fail independently. Failing independently means we have two child coroutines here. If one fails, throws an exception, then this exception should not have an impact on the other child coroutines. If this exception gets thrown, this second coroutine should actually not be cancelled. That is what supervisor job says. But if we execute this, and I just created a dummy instance here of this profile view model and call this function. If we execute this and take a look in logcat, let's clean this up, then you can see down here, coroutine null, okay, it had no name, but coroutine null failed with runtime exception, oopsie. What does this mean? If we take a look here, this coroutine exception handler just catches all the exceptions that are thrown here somewhere in this coroutine block since we've added it to the context. And our exception is thrown after 2 seconds. And after 3 seconds, we expect to see our log that the second job is done. But if we take a look, we don't see this job. Even though we added the supervisor job here that actually says children of this scope should be able to fail independently. So the failure of this first coroutine should not have any impact on the execution of the second coroutine. In other words, we still expect this println statement to be there in logcat, but it's not. Why is that? Well, it's because of a misuse of supervisor job. So with coroutines, we have those contexts, which an exception handler belongs to, the job belongs to, the dispatcher belongs to that, and some more. We can combine those contexts with a plus operator. However, jobs specifically are the only type of coroutine context that is not inherited to the child coroutines, because every single coroutine in Kotlin just has its own unique job. And that job is automatically created when that coroutine is created. And if we now explicitly pass in such a supervisor job or some kind of other job reference to a particular coroutine we launch with launch, what happens here and how Kotlin treats this is it takes the supervisor job, because, as I said, every coroutine still gets its own independent job. It takes the supervisor job and it kind of creates a parent coroutine with that. So what we in the end get is a launch block here, which uses the supervisor job that we've added. And inside of this launch block, we have this view model scope launch block that uses the exception handler. So this is the kind of internal hierarchy that Kotlin will create here. But what this means is that because this supervisor job coroutine becomes a parent of our other coroutine, because the job is not inheritable, this job will not be inherited to this coroutine, it will not be inherited to this one, and also not to this one. All other coroutine contexts are inherited, but the job is not. So while our very outer coroutine uses the supervisor job, the inner one that nests those two calls is not. So you don't get this behavior with the supervisor job that this coroutine here can fail independently of this one, or vice versa. That is why you should actually never really pass in the supervisor job or any type of job at all directly to a coroutine context for a launch function or also for a with context function. So this is something you should not do. How do you now get this behavior? Well, you need to go in here and use the supervisor scope we've also used previously here in the video, and then move this in here, because then these launch functions here, they relate directly to the supervisor job. And now if we relaunch this, take a look here, then we will see, okay, first coroutine is still cancelled, but now we get the println statement that the second job is done. So the second job was not impacted by this exception that was thrown here and called in the exception handler. Another place where it's completely fine to use supervisor job is, as I showed you here before, for coroutine scopes you create on your own. Because then coroutines that are launched in that scope can still fail independently, and that will work if you create a coroutine scope with supervisor job. So that means, for example, remodel scope is also using such a supervisor job. If we have two such independent coroutines launched in view model scope, then this coroutine and this coroutine can fail independently, and that will also work completely fine here. But if you have such child launch blocks and you pass the supervisor job as a coroutine context argument here, won't work. So I hope you learned something here. I deep dive into such things in my Kotlin Coroutines and Flows Masterclass, which I will include a link down below. But most importantly, I also create a link down below for the new Architecture Masterclass, which again, you can get for free, 14-hour premium course. If you are a member of the Mobile Dev Campus, there is still a discount going on for joining the campus until Sunday this week. So check it out and happy learning. See you back in the next video. Have an amazing rest of your week. Bye-bye.